Please welcome to the podium from the Woods Hole Oceanographic Institution, Scott Doney.
Good morning. Ladies and gentlemen, it's my great pleasure to introduce the Ocean Acidification Panel. We have Carol Turley from the Plymouth Marine Laboratory, Ove Herr Goldberg from the University of Queensland, Alexis Valori Orton, a Thomas J. Watson Fellow, Bill Dewey from the Taylor Shellfish Farms, Yim Nang Golbu from the Palau International Coral Reef Center, and Phil Williamson from the Natural Environment Research Council. This amazing group of individuals is going to talk to you today about the science, problems, and solutions surrounding ocean acidification. We'll explore how ocean acidification is changing the chemistry of the sea and also affecting marine ecosystems, how this is then in turn affecting coastal communities and aquaculture, and a series of solutions through improved science and better management. Our first presenter today is Carol Turley, a world leader in ocean acidification research. She will describe how rising levels of carbon dioxide in the atmosphere are changing the ocean chemistry. Carol?
Thank you. Distinguished guests, young people here, and also, I believe, in the United Kingdom at the US Embassy there's 150 other school children participating in this online. So what is ocean acidification? It's very simple. It's due to the atmospheric CO2 levels that we're emitting through the burning of fossil fuels. Oh, we've got the wrong slides. So I'm going to go through these. These are Earth slides. Hey, just bear with me.
Why don't you just talk on and we'll get the slides fixed.
Okay. Do it without the pretty pictures. Okay, CO2 in the atmosphere. We're burning fossil fuels. About 90% of the increase in our emissions to the atmosphere is caused by fossil fuels. Half of that approximately stays in the atmosphere and causes global warming. The other half is taken up more or less equally by the land and by the ocean. So around 27% of our CO2 emissions are taken up by the ocean. There we go. Oh, and when you add CO2 to seawater, you get an acid. It's a basic chemical reaction. And when that occurs, you have a range of other chemical reactions. So the basic carbon chemistry of the ocean, in which all these organisms that we've been talking about over the last day live, is changing. So their environment is changing very quickly. And we know it's happening. This is the atmospheric CO2 emissions increasing over the last decades. And as that occurs, you have equivalent increases in the CO2 in the seawater. And this drives the pH, the measure of acidity, down. And we're measuring these now, so we know it's happening. But it's happening at such a rapid speed that it really is of concern. If it was happening over several thousand years, there'd be no problem. The oceans would buffer it out. But it's happening over just a couple of centuries, and that's what's really scary. If you see this graph, it's actually going backwards in time, and you can see the speed of change that we're going through today and will go through in the future hasn't been seen on planet Earth for millions of years, possibly 65 million years when the dinosaurs died out, or even 300 million years ago. So what we're doing now is just unprecedented. It's just amazing. It's scary. And if we go back to when man sort of created the Industrial Revolution, but 1850, and we really started burning fossil fuels in earnest to fuel our development. Between now and then, there's been a 30% increase in the acidity of the ocean. And if we keep on doing what we're doing, by the end of this century, it'll be between 100 and 150% increase in acidity. So amazing changes. And it's across the whole global ocean. However, there are early, could we go back one, please? There are early vulnerabilities, and this includes the polar oceans, which are naturally cold and therefore take up more carbon dioxide. And some of the waters there are acidifying already, and we're seeing effects on organisms that are actually currently living in those waters. Other vulnerabilities are the upwellings off the coast of this country, of the west coast of North America. We're seeing additional impacts from acidification due to upwelling, and we'll hear more about that later. And also early vulnerabilities could be estuaries and the waters that alongside the estuaries. So if we keep on doing what we're doing, which is the red arrow here and the red line, business as usual, burning fossil fuels like we're doing at the moment, then we're going to end up with a world that is between 3 and 6 degrees warmer, climate change, global warming, but we're going to end up with seas as well that are not only warmer but are more acidic, between 100 and 150% more acidic. However, if we're good citizens and we get together and we have leadership globally and we all pull our weight, both as individuals and as nations, and we look to target between a 1 and 2 degree rise in global average temperature, we will reduce the amount of acidification. Some will still occur, but it will be greatly reduced. So the less CO2 in the atmosphere, the less acidification. So ocean acidification is happening now, it's happening rapidly, and it's happening at a speed that we haven't seen for millions of years. And we can actually do something about it. We have the means, if we act urgently, to make a real difference to ocean ecosystems and everyone living on the planet. After all, the ocean is what makes Earth different to all other planets. And we should bear that in mind. It truly is our life support system. I'd like to thank you all for listening, and my apologies for the mix-up with the slides, and also to the scientists that have contributed to our knowledge to be able to summarize ocean acidification so well. Thank you very much.
Thank you, Carol. Our next speaker is Ove Herr Goldberg. He's an expert on the impacts of ocean acidification on coral reefs. He'll be talking to us today about how changing ocean chemistry is affecting marine life. Ove.
Thank you.
Thank you.
Well, Secretary Kerry, distinguished guests, ladies and gentlemen, given the importance of the ocean to humanity, I think understanding the sort of chemical changes that Dr. Turley was talking about couldn't be more important. So in the next 5 minutes, I want to give you a snapshot of what we know and what we don't know about the impacts of ocean acidification on marine and human systems. Now, there are 3 issues that concern biologists when it comes to these changes. The first is that the rate at which it's occurring is now the highest for the last 65 million years, if not the last 300 million. So we're now taking life outside the conditions that it actually evolved for. The second is that the time frame of coming back from this is around 10,000 years or more. And to put that in perspective, that's our entire history in terms of going from the Stone Age to the present. So this is a really long period of time to pass on a broken ocean to future generations. We're not talking about grandkids, we're talking about 300 generations of humans. And if we don't like what we've done, we've got to live with that. Now, the other issue is that there's now a mountain of undeniable evidence that ocean acidification is affecting the health and distribution of organisms and ecosystems. Whether it's the juvenile stages of commercially important oysters, or it's the plankton that nourishes the great fisheries of the world, there's evidence of major disturbances across the ocean from warming and acidification. Now, this is just one example. This little creature called a pteropod, or a sea butterfly, and it has a tiny shell made of calcium carbonate that's absolutely crucial to its biology. But you see, this one is pitted, and all those little pit marks are from an ocean that's become corrosive to its skeleton. And of course, in many ocean regions, these organisms are disappearing because they can't make their shells anymore. And of course, this has great concerns for many of the great polar fisheries and subpolar fisheries that depend on these organisms for food. So actually, they're the food of thousands of other organisms, including rather charismatic animals such as this bowhead whale. So you're taking out a major component of the ocean and changing it forever. Now, the great fear, of course, is that these changes that we drive will change all the interactions. So there are now hundreds of experimental studies that show that organisms and ecosystems, a whole range of organisms, including corals, calcifying algae, plankton, shellfish, and sea urchins, are all showing changes. And these are components that, like this California kelp forest, are actually crucial to the way that coastline works. And as the water is acidifying around them, they're having trouble forming skeletons, reproducing, growing, communicating, and navigating around marine habitats. Now, this chemical unraveling of these ecosystems has implications for humans. Now, one of the ecosystems that I've worked on that shows this most graphically are coral reefs. Now, coral reefs are pretty amazing places. They occupy less than 0.1% of the ocean's surface, yet they contain 1 in every 4 species of marine organisms. And collectively, they nourish billions of people. And this is their story in pictures when you warm and acidify oceans. So on the left-hand side here, you have a reef today. But as you increase CO2 and temperature, you get more bleaching events, corals don't bounce back from disturbances, and it doesn't take long before you get to that third panel, where all of the ecosystem services that are provided by coral reefs have disappeared, and those people that were depending on them are now vulnerable. Now, this next movie, if we can have the movie, is from Dr. Katharina Fabricius, and it's a living example of CO2 seeps, high CO2 oceans in Papua New Guinea, where you've got literally CO2 bubbling out of the substrate. And so outside these seeps, you have fairly healthy reefs, lots of structure, lots of species. But when you get closer to those high CO2 levels, such as we're seeing now, much of the diversity has disappeared. When you look at the corals, they're quite sparse. there's only a few types of fish that live there. And if you look inside those big lumps of coral that normally are big masses of calcium carbonate, that limestone-like substance, you find it's all corroded away. And these are the conditions that we'll see at the end of this century, mid to late century. This is where we're going. So when you look at so we'll go off the movie now. So in summary, changing the fortunes of ecosystems at this scale has huge implications for human livelihoods and employment. In the short term, there are already documented serious threats to aquaculture, fisheries, and ecosystems that support the livelihoods of hundreds of millions of people. Over the longer term, there is a really serious concern that we're starting to interfere with some very basic processes in the ocean, the food webs and ocean systems that include the plankton, as we've heard, that provides much of the food and oxygen that we breathe. And there is also a concern that if we don't like what we do to the oceans, there's no going back for at least 10,000 years. And these risks and long-term consequences, in the opinion of the most qualified experts, are not worth taking. And if there's one thing that these experts all also agree on, and that is the need for rapid and deep cuts in the global emissions of CO2, because after all, nothing less will solve this diabolical problem of ocean acidification. Thank you.
Thank you, Ove. Our next presenter, Alexis Valori-Orton, is raising awareness about ocean acidification through environmental education. She will describe her firsthand experiences of how ocean acidification is impacting communities around the globe. Alexis?
Thank you. Good morning. I am a young biologist, and when I first learned of ocean acidification, I was shocked and captivated. I wanted to learn more, and so last year I traveled on a Thomas J. Watson Fellowship, studying how this problem might affect people around the world. I lived and worked with communities in Norway, Hong Kong, Thailand, New Zealand, the Cook Islands, and Peru, and I saw just how far-reaching ocean acidification's impacts could be. Today, I want to share with you what I learned. Though ocean acidification occurs in the sea, its potential impacts spread far onto land. Sechura is a town in the far north of Peru, known for its scallop farming industry. Scallops, like all shellfish, require calcium carbonate to build their shells. As we have just heard, ocean acidification decreases the amount of calcium carbonate in the water, harming the ability of shellfish to form their shells. If the scallops in Sechura suffer as a result of ocean acidification, thousands of people will be affected. Divers spend up to 7 hours a day underwater harvesting scallops. Workers on boats haul and sort the harvests on board, and guards who live on the bay for weeks at a time keep watch at night. On land, men sew lantern nets that hold young scallops. Men on docks carry sacks of scallops on their back, loading them on trucks set for processing plants. These plants, as far as 4 hours from the dock, each employ hundreds of people who work into the night, shucking, cleaning, and packaging the scallops. But the impact of scallops in Sechura does not stop there. Hundreds work as a fleet of informal taxi drivers, shuttling divers and deckhands from the town to the dock 40 minutes away. An entire hospitality industry has emerged in Sechura. Buses, hotels, restaurants, all came from scallops. Artists in nearby tourist destination Mancora take the scallop shells and sew them into purses or elaborate lamps. But no one said it as well as a man I met in the fruit and vegetable market. He was selling produce, and when I asked him what he thought about the value of scallops to Sechura, he said to me, "Si no hay conchas en Sechura, no hay nada." If there are no scallops in Sechura, there is nothing. In Aitutaki, in the Cook Islands, the whole island is vulnerable to ocean acidification. This beautiful island and its stunning lagoon is protected by a coral reef. Powerful ocean waves break on the edges of the reef, leaving the shores of Aitutaki still. and calm. Coral lines the beaches, and over time, that coral becomes the fine sand that thousands of tourists run their fingers through every year. An officer in their Ministry of Tourism told me that tourism accounts for 95% of their GDP. But this is about more than just the tourism industry. This is about their home. If the coral protecting Aitutaki is damaged by ocean acidification or other pressures, the entire island is at risk. In each place I visited, I was shocked by how few people had heard of ocean acidification. Those who have the most to lose have no idea what they're up against. And if these communities don't understand this impending crisis, there's no way they can adapt or survive. When I spoke with shellfish farmers and fishermen around the world, they all had questions for me. Why are our oysters dying? They would ask. The water is changing. Can you tell me what is happening? But I couldn't answer their questions because in almost all cases, there was no data available in the areas where these people worked to indicate whether ocean acidification or something else might be causing their problems. Even in countries with excellent scientific research on ocean acidification, those dependent on marine resources had minimal knowledge and access to data. In most cases, no local scientists had even looked at how ocean acidification might affect the very resources that those nearby them depended on. These were the two major challenges I saw. First, that ocean acidification could have such far-reaching impacts so as to topple the extended economy of a village or an entire island. But secondly, those most at risk have no knowledge of what is happening and no access to data or technology that could help them adapt. It is crucial that we work with marine-dependent communities to help them understand ocean acidification and to answer the questions that they have. I hope that all in attendance today will return home, identify these communities and industries at risk, and begin working with them. If we do this, we can concentrate our efforts where they will be most useful, strengthen these vulnerable communities and ecosystems, and build in the capacity for adaptation. Thank you.
Thanks. Thank you, Alexis. Our next speaker is Bill Dewey, who works for the largest producer of farm shellfish in the United States. He will describe how the shellfish industry in the United States is adapting their business practices to address the problems of ocean acidification. Bill?
Thanks, Scott. Well, thanks, Scott. So I've been a shellfish farmer in Washington State for 30 years. Washington State is the other Washington here in the United States, so in the Pacific Northwest corner of the country, so think Seattle. I'm very honored to be here today. I'm going to talk briefly about shellfish farming on the U.S. West Coast, how ocean acidification is impacting us, and what we're doing about it. I work for Taylor Shellfish Farms. The Taylor family's been farming shellfish for 120 years in Washington. To give you a sense of what I'm talking about when I refer to shellfish farms and what's at stake when I speak about the impacts of ocean acidification, these are some photos of our farms and the products that we grow. So besides working for Taylor Shellfish, I also have a farm of my own that I produce about 80 tons of clams on every year. The two lower right-hand photos are from my farm. The machine I'm operating is a tulip bulb harvester imported from Holland that I've modified to harvest clams. So when the tide is high, the land that you see there is under 3 meters of water. So I share those photos just so you know that I have a personal stake in this ocean acidification issue. Taylors have two shellfish hatcheries. Go back, please. Taylors have two shellfish hatcheries, one in Washington, one in Hawaii, that we produce our baby clams and oysters in. We refer to them as seed. The first few weeks of an oyster or clam's life is spent as plankton, free-floating in the water. At this point in their life, we've learned that they are the most vulnerable, particularly to changing seawater chemistries. Starting around 2006, our Washington State hatchery and another hatchery on the Oregon coast started to see significant and repetitive oyster larvae mortalities. It took a couple of years to figure it out, but with the help of scientists from the United States government and various universities, we soon learned it was the changing seawater chemistry caused by the ocean absorbing carbon dioxide emissions that was contributing to our hatchery failures. So an outcome, as we've heard, of this phenomenon known as ocean acidification is reduced calcium carbonate ions. Not good news if you're an oyster. These are the building blocks for your shells. So these high CO2 waters, low in carbonate ions, are stored deep in the Pacific Ocean, and when we get northerly winds on the US West Coast, they come to the surface, into our estuaries, and then we pump them into our hatchery. We've learned from the Oregon State University scientists that in the first 48 hours of life, 90% of an oyster's weight gain is shell. It does this with energy that's stored within the egg. So with fewer calcium carbonate ions in the water, it has to work harder to build this shell. And as a result, the shell is deformed, as you see in the photograph on the right. And more critically, it doesn't have enough energy left to build the feeding organ that it needs to feed with. So here you can see that feeding organ. It's called a velum, a very critical organ for the oyster larvae at this stage. So because of the effects of ocean acidification, during 2008 and 2009, oyster larvae production at 2 of the 4 West Coast hatcheries was down by 75%. This created a big shortage of oyster seed for our industry and had a very severe impact. As you can imagine, this created some panic among shellfish growers. And in response, we ramped up rapidly research and monitoring. We increased the production at our facility in Hawaii, where we had not been seeing the same effects. We also installed sophisticated monitoring equipment, so we're able to see the corrosive water coming at us and either dodge it, or as we've learned, now we can treat it by adding sodium carbonate to increase the carbonate ion concentration in the water. These actions have allowed us and the Oregon hatchery to recover a significant portion of our lost production. Washington State's governor formed a blue ribbon panel that delivered 42 recommendations to her in 2012 on what we could do as a state to address ocean acidification. So in summary, ocean acidification is real. It's impacting our shellfish and other species now, and because of it, we're going to witness a very different ocean and in our lifetimes. The world needs to grapple with carbon dioxide emissions, and while we do, as you've seen from my example, there are actions we can take to adapt and mitigate the impacts to our oceans that in the short term can help. In closing, last year the Seattle Times published a 3-month series of coverage on ocean acidification. That's what you see the photo of there. It's available online at that website, and I brought copies of it. They're out in the courtyard. I encourage you to take a look at it. It's very thought-provoking and informative. So as world leaders on ocean matters, I hope you can help us address this very serious problem of ocean acidification. Thank you.
All of them. Those are mine.
Oh, sorry.
Thanks, Bill. Our next speaker is Yingnang Golbu, who's helping to conserve and protect the coral reefs of Palau. And he will discuss how some of the lessons that they're learning in Palau could be adapted and used around the world for other coral reefs.
Good morning, ladies and gentlemen. It is an honor for me to speak to you today. Palau is a small island in the Western Pacific, which is surrounded by beautiful coral reefs. Coral reefs have provided generations of Palauans food resources and important services, such as wave protection. Many of our islands, including our iconic rock islands, are made by reef corals. More recently, coral reefs have become a major contributor to the economy of our islands. Over 80% of the visitors who come to Palau come to dive and snorkel on our coral reefs. These beautiful coral reefs are making tourism our #1 industry in Palau. Coral reefs are not only important to Palau, but also important worldwide. They support 1 billion people, hold 1/4 of all ocean life, and generate $375 billion per year. But in spite of their importance, coral reefs are facing many threats. One of the main concerns for coral reefs is the threat of ocean acidification. The impact of ocean acidification on coral reef organisms have been well demonstrated in laboratory experiments, but not as well in the field. With the discovery of carbon dioxide vents in Papua New Guinea, with acidity around those vents having the same values as what is predicted for the end of this century, scientists are able to see how coral reefs might be affected in the near future. Studies around these carbon dioxide vents show that there are fewer corals, lower diversity, and fewer calcifying organisms than on the reefs of today. But is this the same everywhere? Or are there exceptions? Or climate change refugia that we can find? The first clue that there would be exceptions or refugia came from our studies of the bleaching event that occurred in Palau in 2010. The water temperatures increased island-wide, causing corals to lose their symbiotic algae living inside them, therefore turning white, in what we refer to as coral bleaching. And since corals depend on the symbiotic algae living inside them to provide them with food, many corals that bleach will eventually die of starvation. During the bleaching event, we found that there were places that got really hot, and yet corals did not bleach as much as elsewhere. The figure on the left shows temperatures around Palau during the bleaching event of 2010. And the figure on the right shows the percentage of corals that bleach around Palau. And when we look at these two figures, we see that there are areas that got really hot and yet did not bleach. These areas are refugia and they are close to the land. Similarly, we found areas in Palau, close to the land, with acidity similar to the carbon dioxide vents in Papua New Guinea, and what is predicted for most reefs by the end of this century. And yet, these areas have the highest coral cover and the most diverse reefs anywhere in Palau and Micronesia. These corals have adjusted and survive in this acidic environment. These are refugia for ocean acidification and ocean warming. So what can we do with this information? Since these refugia are close to land, they are under threat from land use change and pollution. We must ensure that these areas are protected and they are incorporated into our existing marine protected areas network. We are now modeling connectivity among the existing marine protected areas in Palau to determine if they are connected with each other. The modeling shows there are still gaps in our network that we are now working to resolve with the Ministry of Environment by adding new marine protected areas to fill these gaps. Our research is also showing that not only do we have connectivity within Palau, we have connectivity with other countries in Micronesia. This is why regional initiatives such as the Micronesia Challenge and other initiatives to expand protection of our ocean are critically important. These efforts will ensure the persistence and sustainability of coral reefs in Palau so that they can continue to provide important resources and services that our people have depended on for generations. Thank you.
Thank you. Our final presenter for the panel is Phil Williamson, the Science Coordinator for the Ocean Acidification Research Program in the United Kingdom. He'll be talking about the need for a coordinated global approach to addressing the problems of ocean acidification. Phil?
Good morning distinguished guests, ladies and gentlemen. If there's one emerging theme from this conference, it's that policymakers need to act on evidence. But that does not mean that the case is closed and that we can stop collecting the evidence. Now, if I only had one slide to show, it would be the one that you'd see on the screen now. What you don't measure, you can't manage. Now, measurement doesn't solve the problem, but it does determine its scale and its nature and helps us to show how it might be addressed. For ocean acidification in particular, there are clear policy benefits in making many more measurements, making it possible to give early warnings of damaging events, establishing whether ocean acidification is responsible for the observed impacts, and providing robust justification for the difficult and long-term policy decisions that need to be made. Ocean acidification measurements are also needed for science, because it's not just for monitoring, not just for data. From data, we need information. From information, we need knowledge. To understanding, to provide the quality, to improve the quality of the scientific advice with regards to the implications of specific policy scenarios for future ocean health. Ocean acidification measurements need to be on the global scale, on a worldwide basis. That's because, as we've heard over the last couple of days, there is only one ocean, shared by everyone on Earth. Ocean acidification is affecting, to some degree, every part of it. The very wide participation in this conference shows the need and the benefits of pooling ideas and information to develop a common approach to address the problem of ocean acidification. That problem, as we have heard from Carol Turley, is primarily caused by what we're putting into the atmosphere. Now, you've already seen this slide, so I'm not going to explain it in any detail. I do, however, want to bring your attention to the fact that the ocean data sets that are shown on the graph are very much shorter than those for the atmosphere. They're also much more variable. Now, that variability can be from place to place in different oceans. It can be quite close geographical regions. It can be within the depths of the ocean. The surface differs from deeper down. But also there can be changes seasonally. On the graph here, I show the long-term changes from year to year and on a decadal basis. But because of this variability, it's not enough just to go out and measure pH or other carbonate parameters. Well, you've got to know exactly what it is that you're measuring, and you've also got to repeat it. So it's a bit like temperature. You don't just go out one day, say, I've taken the temperature, I know what it is from where I am. You've got to keep it. You've got to do it consistently. You've got to do it accurately. You've got to do it over many months, repeat it day and night, over a considerable period of time. Now, here's an example of one ocean data set for pH showing the variability at one coastal site over a couple of months last spring and summer. And this is from the west coast of America, and many of you recognize it. Bill Dewey's farm. I should have put it on the map, but it's up near Seattle, up at the top of the map. Now, that's just one data set, and the color change there shows how pH went up and down at one particular site. Now, it happens that this was part of a program, and they were not just measuring pH at one coastal site, they were measuring it at 6 coastal sites. Because they were measuring it in the same way, you've got 6 data sets that are comparable. Because they're comparable, you can put the information together. You can combine it and get one picture, and then you realize that there's a pattern, that they're all changing in a consistent way. And if you make other measurements, not just of the pH, if you measure some of the weather factors are going on, and at the top of the graph you'll see the wind strength and direction. And there is a very close match in this particular part of the world of the short-term variability between the wind strength and direction and the changes in pH. That was alluded to by Bill Dewey. Now, this gives short-term forecasting capability, but that relationship doesn't hold everywhere in the world, and there are also lots of other factors that change the pH, change the carbonate chemistry from week to week, month to month. And by putting together the information from lots of other places, measuring pH in different ways, we now can put together the start of a global map. And on the global map, you'll see for the yellow dots are where the chemistry is being measured. The blue circles are where the chemistry has been measured at specific sites for 5 years, Now, there's not many places with blue circles around them, just 8 on the map. What we need to do is to link that chemistry with the biology. And we need to do it not just in a few places where we've got the expertise, but there's large areas on that map where hardly any measurements are being made at all. So that's where we need to be. That's where a global ocean acidification network needs to be developed to sustain and take forward the observations. Now, yesterday we saw from Margaret Linen, Argo floats. Haven't got any time to go into any detail for this, but this is a way of making additional measurements, putting them together. We need the coastal measurements as well, and we need to put that together, and we need to carry on making those measurements long-term, chemistry and biology, a sustained global partnership to take that forward. Thank you very much.
Thanks, Phil. Thank you, Phil. In our next section, we'll be opening up the floor to our audience, both here in the room and online. As Carol already mentioned, we have some 150 students gathered at the U.S. Embassy in London. There are other groups gathered around the world listening to us. So we will be opening up. If you're online, you can connect with us using social media, using the hashtag OurOcean2014. Before we take questions, I understand that there are a couple of announcements from a few members of the audience. So I'd like to start following up on Phil's talk about a global observing network. I believe Mark Spalding, the president of Ocean Foundation, has an announcement he'd like to make. Mark?
Thank you very much. Again, my name is Mark Spalding from the Ocean Foundation, and as the panel illustrated, we've identified a major threat to the ocean in ocean acidification. We've identified that a key element of responding to that threat is monitoring and observing what is going on. Alexis, Bill, and Phil all made clear that there are gaps in that response that are huge, and that we need sustained funding to leverage that. I am pleased to announce today that we have formed a Friends of the Global Ocean Acidification Observing Network account at the Ocean Foundation with 5 founding donors contributing to it so that we can begin to collect and provide sustained funding so that the network can be expanded, implemented, and effective. Thank you very much.
Thank you. Next, I believe Dr. Kathy Sullivan, the administrator of NOAA, has a couple of announcements on behalf of her agency. Kathy?
Thank you very much. We've heard compelling stories today about the need for improved monitoring and coordination at all scales and consistently through time to understand, to strengthen the science, and to begin to equip ourselves to make better decisions with respect to ocean acidification. I'm pleased to announce that NOAA is investing more than $9 million over the next 3 years to sustain the Global Ocean Acidification Observing Network. This is one of the vital efforts that will help us better understand the patterns, the trends, the status of ocean acidification at all time and space scales to improve our science and help us progressively make sounder decisions. Second announcement has to do with collateral benefits of coastal ecosystems, some of those same ecosystems that are affected by ocean acidification. Seagrasses, mangroves, wetlands, tidal marshes, and more. We know that these ecosystems sequester large amounts of carbon. Restoring them can improve the globe's capacity for carbon sequestration, becoming a win for blue carbon, for the productivity of fisheries, and for our coastal communities that will be better protected from natural hazards. So our second announcement on this front is that working with the United States Environmental Protection Agency and Canada through the Commission on Environmental Cooperation, we will invest $450,000 over 2 years in the first North American effort to strengthen the science, the regulations, and the economics of blue carbon in order to incentivize additional habitat protection and restoration. We invite our partners here today to join us in these investments. Thank you.
Thank you, Kathy. Last but not least, the Department of State's Assistant Secretary Tom Countryman has a few words. Tom?
Okay. Thank you. I'm Assistant Secretary of State for International Security and Non-Proliferation. In 2010, the International Atomic Energy Agency established the Peaceful Uses Initiative to raise voluntary contributions in support of activities that promote peaceful uses of nuclear technology. I'm pleased to announce today that under this initiative, the U.S. Department of State and the U.S. Department of Energy will contribute $1.9 million in funding to support projects to address ocean and marine issues. These include ocean acidification, marine pollution, climate change, seafood safety, and marine and coastal environmental monitoring. This additional funding will bring the overall United States contribution to marine and ocean issues under the Peaceful Uses Initiative to more than $3.4 million since 2010. The U.S. wants to encourage all governments to explore with the International Atomic Energy Agency how they could contribute to peaceful uses projects that would address critical ocean and marine environment issues. Thank you.
Thank you. Thank you, Mark, Kathy, and Tom. Those are all very exciting developments.
Provide big benefits if there is an opportunity to move operations to an area of lower acidity, and provide big benefits if there's an opportunity to intervene to control the chemistry in an environment you can control, such as certain kinds of aquaculture facilities. But what I'd like to probe a little bit is what our adaptation options are going to be as the process of ocean acidification proceeds, and there are fewer places to go to where the acidity is low enough to be tolerable, and where the impacts in the ocean as a whole become problematic, and one doesn't have the option really of altering the chemistry of the ocean as a whole as opposed to altering the chemistry in a limited aquaculture facility. So I'm just wondering what the sense of the group is on how our adaptation possibilities will change going forward.
Thank you. Ove, do you want to start with that, and then maybe Bill?
Yeah, so I think it comes down to the fact that if you take the physiology of marine organisms, these are fundamental changes, you know, pH, carbonate ion concentrations. So nothing less than actually changing the chemistry of the ocean is going to really make a big change. I think as we saw with the examples in Palau, that there could be pockets where you take other pressures off reefs and you improve their ability to bounce back. So there may be, you know, it's a sort of an adaptation option of reducing stress and then protecting some regions. The trouble is that when you get to the end of the century and we haven't constrained CO2, I think we get to places where I think there won't be any places in Palau. Temperatures, of course, will be 3 to 6 degrees, as we saw from Dr. Turley. And so in that scenario, I think adaptation disappears as anything meaningful. You're right, aquaculture, I think, treating water, there's some clever ways, perhaps with marine plants, to buffer the different types of chemistry, but that's really at the scale of acres, not, you know, the enormous amount of upper ocean that we really need to start to change. So it comes down to deep and fundamental cuts in emissions.
Bill, do you just have a few thoughts?
Yeah, I don't know what I'd have to add to what Ove said. I mean, these are all, what he mentioned are things that we're considering with our ocean acidification blue ribbon panel in Washington State, you know, looking at seaweed culture, restoration of sea grasses and so on to create localized areas, you know, that have some buffering and protection, but on a grand scale, we really need to deal with the source of the problem.
Thanks. We have a team of students from a local high school, Thomas Jefferson High School for Science and Technology, and they did a project on ocean acidification for the National Ocean Sciences Bowl this year. I'd like them to introduce themselves briefly, and if they could ask their question.
Hi, I'm Rachel Zoll.
Hi, I'm Christopher Chen. I'm Jared Nuremberg. My name is JC Panagidis.
And good morning. I'm Comfort Sampong. Effective responses to ocean acidification are multifaceted and necessitate this integration of policy with real-world outcomes. Currently, we are at a crossroads regarding the international community's ability to deploy monitoring systems, enable data sharing, archiving and analysis, and implement policy. How can local and international stakeholders support efforts to collect data and better monitor changes in the ocean and atmosphere? And how can this information be better communicated to decision makers in local, national, and international governments? Thank you.
Thanks. Phil, do you want to take a crack at that?
Well, thank you very much for the question, but I think you almost gave the answer to it in the last few words, in that you mentioned the collaborations and the partners and the groups involved, and it is communities, it is national governments. I mean, there's a very major responsibility for national governments. There's intergovernmental bodies, the UN bodies, there's also the research scientific community, there's private sector, there's a whole sort of series of different organizations that have got interests, and that they are all talking to each other. We have made a start for this Global Ocean Acidification Observing Network. Really only began a couple of years ago, and we've talked about it, that there was the need for it 4 or 5 years ago. But it's only in the last couple of years that the scientific community has come together with the support of governments and intergovernmental bodies. Now, that's got to go out. There's a lot of people in the world who don't know about it, who we need to engage with. That needs resources, needs effort, but at lots of different levels. So it's an excellent question. It's not quite so easy to solve it, but those are the steps along the way that we need to take. Thank you very much.
Phil, we had a follow-on on Twitter from Chad Nelson, and he wanted to know, how could a citizen, how could a volunteer go out and monitor ocean acidification in their backyard?
That's a little bit tricky, because in order to have really reliable measurements, I mean, one can do it crudely, but really to have the measurements that have value, because of this variability, it isn't quite so easy for everyone to do it themselves. So I think it's getting in contact with local research centres and universities. There may be projects and opportunities to get involved with there, but it isn't something that one can have a go at it, but it isn't something that individuals can. Perhaps the scope for individual involvement might be actually more on the biology and the impacts and the changes that might or might not, and then to have the chemical information to say, well, what is causing these particular changes? Because it might be ocean acidification, it might be something different, but to have the wider network of observing of natural history and biology, that might be the major input that can be provided.
Thank you, Phil. I think we're going to have to cut off, I apologize, we're going to have to cut off the questions right now, but I'm sure the panelists would be more than willing to talk to you at length at the coffee session. I want to thank all the panelists for their wonderful presentations and discussion on the problem of ocean acidification, how rising atmospheric carbon dioxide levels are affecting the ocean, both through the chemistry and the biology, and what a range of possible solutions are on local and regional scales. At this time, I'm going to invite Ambassador Bolton back to the stage and turn it over to him. Thanks.
Very well done. Good morning, ladies and gentlemen. Good morning in particular to the students from Thomas Jefferson. Welcome back to the State Department. It's good to see you again. You guys are my heroes. Earlier this spring, another group of high-level diverse people gathered in the Netherlands for the Global Oceans Action Summit for Food Security and Blue Growth. I had the pleasure of being there, and I know a number of you were with me there. Sharon Dijksma, the Minister of Agriculture of the Netherlands, presided over this summit, which her government organized in close collaboration with the Food and Agriculture Organization of the United Nations and the World Bank and a number of other governments, including mine. In a moment, we will see a short video from Minister Dijksma summarizing the main outcomes of the Global Oceans Action Summit. I want to say that because we're running a little late today, we're going to have to shorten the break just a little bit. After the video, we will have a break, but please be back here at 11 o'clock. Thank you very much.
Dear ladies and gentlemen,
Thank you, Secretary of State Mr. John Kerry, for this opportunity to highlight the outcomes of the Oceans Action Summit, which was hosted last April in The Hague, the Netherlands. We need healthy oceans more than ever, but at the same time, ocean health is threatened by 3 issues: habitat change, pollution, and overfishing. And we ourselves are responsible. This responsibility has to be turned around into action, and that takes courage. So the question is justified. Do we dare, ladies and gentlemen? Do we dare to grow smarter? Do we dare to fish smarter? And are we really willing to stop the moral outcry that still almost 1 billion go to bed hungry every day? Then we have to act. Then we need a new way for the world. This was the slogan of the Global Action Summit in The Hague, organized by World Bank, FAO and the Netherlands. What were the outcomes of our chair's summary report? The foundations for you to build upon. First of all, that we should learn from concrete success stories. Competing interests between economy and ecology can be reconciled. We should identify actions, partnerships and new finance structures. Then, fish knows no boundaries. Governments play a key role in addressing the challenges, but regional cooperation through regional fisheries management organizations is becoming even more important. The Hague Summit pointed furthermore at the important role of local communities. Strong momentum exists to reshape the context in order to ensure sustainable growth with equitable benefits for communities. Last but not least, we can significantly increase food fish production and blue growth from sustainable aquaculture and fisheries. If we use these approaches, we can halve the current rate of natural habitat loss, increase marine protected areas to include at least 10% of coastal and marine areas, and we can conserve or even restore natural coastal habitats to reduce vulnerability to climate change impacts. Moreover, the high-level segment called for embedding oceans in the post-2015 development framework, preferably in a standalone sustainable development goal for the more equitable use and access to benefits from marine resources. Ladies and gentlemen, the set of action needed is clear. We must make progress now, and I trust that's what you'll do the coming days. I wish you all the success and inspiration with that. Ladies and gentlemen, we will continue with the conference after a 15-minute break.